A half adder, one of the combinational circuits that is used to add single bit numbers. It does not take carry from the previous sum. A logical circuit that takes an input of 2 bits and provides an output of 2 bits as the sum and carry terms is called a half adder. Output here is only dependent on the present input. So here the output depends on A and B. How does a half adder work? As we know, A plus B equals to sum, which is 0 plus 0 equals to 0, and the carry, which is C out, is also equals to 0. In other case, when A is equal to 0 and B is equal to 1, then the sum is 1 and the carry still remains 0. Next case is when A equals to 1 and B equals to 0. Then the sum is 1 and the carry remains 0. When A equals to B equals to 1, then the sum is 1 plus 1, which is 2, and it is written as 0 in the binary, and the carry here is 1. What is the logic? As we have seen in the circuit, there it represents S equals to A XOR B, which is A bar dot B or A dot B bar, and the carry is given by A dot B. The ins and outs of half adders. A flip-flop can be used to output a carry bit that only has 2 inputs. Therefore, it cannot be used for binary calculations where there may be a carry from a previous calculation. For example, 0, 1 plus 1, 1 is 1. But there remains a carry which cannot be further added in a half adder. Full adders. In case of half adder, we do not accept carry from the previous sum, but in case of full adder, we do accept the carry from the previous sum. Full adders are the combination of two half adders where there can be 3 inputs from the user, that is A, B and Cn. They make a sum and a Cout connected to an OR gate. The gate diagram of the full adders is as follows. There is a half adder which is further connected to a full adder and then which gives sum, and a Cn is connected to the next half adder which gives Cout. The complete truth table is as follows. Here the 0 plus 0 plus 0, which is A, B and Cn, is 0, and the Cout, which is carry, is also 0. In the next case, 1 plus 0 plus 0 equals to 1 and the carry is 0. Adding the other 3 numbers, that is A equals to 0, B equals to 1, C equals to 0 gives 1 as sum, and Cout will be 0. Next we add A equals to 1, B equals to 1 and Cn equals to 0. Then the sum will be 0 and the carry will become 1. Next possibility can be 0 plus 1, that is A equals to 0, B equals to 0 and C equals to 1, which gives sum as 1 and carry as 0. Next case is 1 plus 0 plus 1, which is A equals to 1, B equals to 0 and Cn is 1, which gives sum as 0 and Cout as 1. When we take A equals to 0, B equals to 1 and Cn equals to 1, then sum becomes 0 and carry is 1. When we add A equals to 1 plus B equals to 1 plus Cn equals to 1, then we get both sum and carry equals to 1. This is the complete truth table of full adder. The sum in a full adder is defined by A XOR B XOR Cn, whereas the Cout here is represented by A dot B or B dot C or C dot A, or it can also be written as A dot B plus Cn bracket A XOR B bracket close. Using full adders. Half adder can be used to add 2 bits, but the full adder has an advantage over it, which adds 3 bits. Here, A and B are input, C is also an input which gives sum as an output and a carry out also as an output. As we know, an adder is a digital circuit that performs addition of numbers. In many computers, adders are used in arithmetic logic units of ALE. Full adder can add a bit carried from another addition as well as the two inputs, whereas half adder can only add the inputs together. That's why we have an advantage of full adder on half adder.
Samyak here, and now today I'm going to explain you RCA and CLA, ripple carry adder and carry look ahead adder. So in a ripple carry adder, carry look ahead adder, we are taking four 2 bits number B3. Let me name them as A3, A2, A1, A0, B3, B2, B1, B0. Uh, these are the inputs I'm giving: A0, B0, A1, B1, A2, B2, and A3, B3. So when we'll add those the numbers, we'll get a sum S naught and a carry C naught. So I am putting it as here as S naught and here as C naught. I am attaching this C naught with the next full adder. So because we need this in addition in C0, A1 and B1. So I am attaching it with next full adder. So now our sum will be S1, C1, S2, C2, S3, and finally C3. So here we'll get C1 and S1, C2 and S2, C3 and S3. These are our 5 outputs which you will get, and this is what a ripple carry adder is. Now moving forward to CLA. CLA is a more defined version of RCA. With we will learn this by this truth table. This truth table has this is of a truth table of carry, and this is of carry, and this one is for sum. So here from this truth table we can see when we get any 2-bit number, when we will add, like when we'll add 0 0, we'll get a carry of 0. When we'll add 1 1, we'll get a carry of 1. So when we'll get two ones or more than two ones, we'll get a carry of 1. So now we'll look at this truth table and understand. Here we get three zeros, so our carry will be 0. Here only one is there, so our carry will be 1 here also. And now here we get two ones, so our carry will be 1. uh, so by this we are getting four positions where our carry is 1. Now we will dive deep into it. After seeing these and this, we can see here A and B, and here A and B are of opposite. So we can from this we can get a formula: A is or B dot C by seeing these terms. For a if this condition is satisfied, we'll get a if this condition by this condition, if we get a answer 0, our carry will be 0. If the answer is 1, our carry will be 1. And by looking at these last two terms, we are getting a condition A dot B. So no matter what the C is, so our next formula is A dot B equals to, if we get 0, our carry will be 0. If we get 1, our carry will be 1. So by using this two formula, I'm making a formula of carry by using this two formula, A dot B plus A XOR B dot C. So this is a formula for carry. We refer this as G naught and this as P naught, because in our in CLA we don't get output as C, we get output as G naught, P naught and sum. Now we'll look at the sum diagram. So we can see directly uh, when there is 0 1, our sum will be 0. When there is 1 1, our sum will be 1. When there is 2 1, our sum will be our sum is 0. Why? Because when we have two ones, our that will go on carry, and the output we get at some position will be 0. So by this situation we can get a formula A XOR B XOR C. That means if there are odd numbers of 1, our sum will be 1. If there are even numbers of 1, our sum will be 0. By now we'll put this in the diagram. This is a C in A naught, B naught, A1, B1, A2, B2, A3 and B3. Now as I said, here our output is sum S naught and P naught and G naught, and this is our carry which we will which we bring up by using that formula C naught. Now here we are getting P1, G1 and carry C1, P2, G2. Here we also get sum. Here sum is S2 and this is C2, then P3, G3, this is our S3 sum, and this is C3. So now this by looking at this diagram we can understand that we are getting output as P naught, G naught and S naught, and by using the formula we can directly see use P naught and G naught to bring out our sum. So these are the two formulas which will help us bring our formula. Thank you.
I'm going to tell you about half subtractor. Now moving towards half subtractor. In this we need two inputs as A and B. This box is a half subtractor. We'll see the gates used in this box later. So here A and B are two inputs. Both A and B are single bit numbers. Here D is the difference and B naught is the B output. In this we are going to see how to subtract two binary numbers and to find out what is the circuit for your half subtractor, which means we need to find out the logical expression. Now let's do the first case and see how to subtract binary numbers. Let's take a binary number. So our first number is 0 1 0 and the second number is 0 1. Now we know the rules of subtraction, so we can easily subtract these two numbers. So for this, but in this case, we cannot subtract 1 from 0 because 1 is a bigger number and 0 is a smaller number. So we'll take a borrow. The weightage of this position is 2 raised to the power 0 and the weightage of this position is 2 raised to the power 1. So we'll take a borrow from this position. So the value of this position will be 2 raised to the power 1. Now we can easily subtract 1 from 2. So the value will come here is 1, and now the value of this position, weightage of this position is 0, so the value here will come as 0, 1. As you can see the subtraction, by using this concept we can subtract we can subtract a and b. We are having two inputs and two outputs. Two inputs are a and b, and two outputs are d and b naught. As there are two inputs, so there can possibly be four cases. So let's make the four cases. So the four cases will be 0, 0, 0, 1, 1, 0, 1, 1. In the first case, we can easily subtract 0 from 0. So the value of difference will be 0 and the borrow output is also 0. In the second case, we cannot subtract 1 from 0. We cannot subtract 1 from 0. So we'll have to take a borrow. So we'll take a borrow. So the weightage of this position will be 2 raised to the power 1. Now we can easily subtract 1 from 2, so the difference will be 1 and the borrow output is also 1. In the third case, we can easily subtract 0 from 1, so the value of difference will be 1 and the borrow output is 0. In the fourth case, the value of borrow output will be 0 and the difference will also be 0. Now we are going to realize D and B naught. For that we need to make a logical circuit, but before that we need to find the value of D and B naught. The value of D and B naught can be found easily by the K map that you can do yourself. So the value of D will be A XOR B and the value of B will be A bar B. You can do it yourself. Now, let's make the logical circuit. For logical circuit, we need two inputs A and B. Let's make a vertical line for A and B. Take a NOT gate from A and make a vertical line again. Take a NOT gate from B and make a vertical line again from A and B. Now we have to make logical circuit for D output. For that we need a XOR gate. We'll make a XOR gate here. For that we want two inputs A and B. So we'll take one input from A and another input from B. The value of D can be calculated by using this gate. And for the value of B, we need a AND gate. Also A bar B. A bar we can take from this position and B from this position. So the value of D and B naught can be calculated by using these two gates. And that will be so easily for us to understand by using these two gates. Thank you guys. I am going to tell you about full subtractor. In this video we'll try to find out logical expression for full subtractor. This is a box. This is a box of full subtractor. We'll see what is inside this. Here A is a number which you want to subtract from B, and C is your borrow from next stage. Here D is difference and B naught is B output. The prime goal is to find out the combination of gates inside the box. So as we have three inputs A, B and C and output D and B naught, there can be possibly 8 outputs. So we'll try to perform subtraction within these three inputs A, B and C and two outputs D and B naught. We are going to use the concept as we have used in half subtracted. So here the 8 inputs will be 8 possible inputs will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. As we can in this, we first we have to subtract b from a and then c from b. As we have subtracted in half subtractor, so we can do easily in this full subtractor also. So in the first case, we have to subtract 0 from 0. The value will be 0. Now C from B means 0 from 0, the value of D will be 0 and B output is also 0. In the second case, first we have to subtract 0 from 0, the value will be 0 and then 1 from 0. Now we cannot subtract 1 from 0 as 1 is a bigger number than 0, so we will take a borrow. We'll take a borrow means here will come 1 and the value of this position will be 2. So now we can calculate subtraction easily. So by subtracting 1 from 2, the value of D will be 1. In the third case, first we will subtract 1 from 0 that we cannot subtract, so we will take a borrow. The value of B naught will be 0 and the value of this position is 2. Now we can subtract 1 from 2, so the value of D, so the value will be 1 and again 0 from 1, so the value of D will be 1. In the fourth case, first we will subtract 1 from 0. For that we have to take a borrow. We will take a borrow. The value of this position will become 2. Now we will subtract 1 from 2. So the value will come here is 1 and now 1 from 1 the value of D will be 0. In the next case we will subtract 0 from 1. So the value will be 0 and again 0 from 0 the value of D will be 0 and borrow output is also 0. In the sixth case, first we will subtract 0 from 1. The value will come is 1 and 1 from 1. Now the value of D will be 0 and B output is also 0. In the seventh case, first we will subtract 1 from 1. The value will come here will 0 and now C from B means 0 from 0. The value of D will come 0 and B output is also 0. In the last case, that means case 8, first we will subtract 1 from 1. The value will come 0. Now we cannot subtract 1 from 0 because 1 is a bigger number than 0, so we will take a borrow. Here will come 1 and the value of this will become, value of D will become 1. So the value of D and B are the value of D is 0 1 1 0 0 0 0 1 and the value of B output is 0 1 1 1 0 0 0 1. You can we need to minimize D and B output. Now we can minimize D and B output by using K-map that you can do yourself. So the value of D and B naught will come as D will be A XOR B XOR C and the value of B output will become BC plus A bar C plus A bar B. This you can calculate by using K-map yourself. Now after finding the values, you need to find a logical diagram for the 3 inputs and 2 outputs. For the 3 inputs, for that we are having these 3 inputs A, B and C. First we will make vertical line from A, B and C, and now we'll take a NOT gate from A and draw a vertical line. Again we'll take a NOT gate from B and make a vertical line. This we will do for C also. For the value of D, which is A XOR B XOR C, we have to make a XOR gate. First we have to make a XOR, wait a minute. First we have to make a XOR gate. For that we need 3 inputs A, B and C. So we will take 3 inputs from here. First input is A, second input is B and third input is C. So the value of D can be calculated by using XOR gate. Now for the value of B output, we can use 3 AND gate and 1 XOR gate. So first we will calculate BC. For that we'll take B from this position. Take B from this position and C from this position. For A bar C, we'll take the input from this position. This is A bar and this is C. A bar C. For A bar B, we'll take the input from this position and B from this position. Now, by using OR gate, we can perform the addition. Of these three inputs. So the value of B0 will come as BC plus A bar C plus A bar B, which you can calculate easily by using these two gates, XOR gate and gates and OR gate. Thank you.
Cut. Now I'm going to tell you about multiplier and how to obtain multiplier circuit and how it works. Let's take two 2-bit numbers A and B, where A is A1 A0 and B is B1 B0. The box here represents the 2-bit multiplier. A and B are represented by thick arrows because they are multi-bit numbers. P is the product that we obtained after multiplying A and B. And the output P is a 4-bit number because when you multiply two 2-bit numbers, the maximum possible output is a 4-bit number. So let's take P as P3, P2, P1 and P0. Now I will tell you how to obtain the values of P3, P2, P1 and P0. We will first multiply the two numbers A and B, that is A1 A0 multiplied with B1 B0. The multiplication will be same as the multiplication of the decimal numbers, that is we will first multiply B0 with A0 and A1 and then we will multiply B1 with A0 and A1. So in the 0th column we have A0 B0 and in the first column we have A1 B0. A0 B1 and A1 B1. Now we will simply add the columns. As A0 B1. So the carry of the first column will go to the second column. So in the second column we have C1 plus A1 B1 and the carry of the second column will go to the third column. So our value for P0 is A0 B0, P1 is A1 B0 plus A0 B1, P2 is C1 plus A1 B1 and P3 is C2. So now as we learned in the half adder, when we add two numbers, let's suppose the two numbers to be A and B, and when we add the two numbers, the sum is A XOR B and the carry is A dot B. So in this case, we'll need one half adder for P1 and one half adder for P2. So let us draw the circuit of 2-bit multiplier. We'll simply write the numbers first, that is A1 A0 B1 B0. Now we'll draw P0. So as you can see that P0 is nothing but A0 B0. So here we'll draw A0 B0. We'll join them with the AND gate and we'll obtain P0, which is A0 B0. Now we'll draw P1, which is nothing but A1 B0 plus A0 B1. A1 B0 and A0 B1. We'll join these two using a half adder. Here we'll have a sum and a carry. This is S1 and the carry is C1. Now we'll draw P2, which is C1 plus A1 B1. C1 plus A1 B1. A1 B1. We'll join C1 and A1 B1 using a half adder. This is S2 and this is C2. This S1 is nothing but P1 and this S2 is nothing but P2. And we know that the value C2 is our P3. So this is the circuit of the 2-bit multiplier. Now similarly, we will multiply two 3-bit numbers. Let the numbers be A and B, where A is a 3-bit number, which is A2, A1, A0, and B is also a 3-bit number, which is B2, B1 and B0. As I told you that P in the 2-bit multiplier was a 4-bit number. In this case, when we have two 3-bit numbers, when you multiply two 3-bit numbers, the maximum possible output is a 6-bit number. So let us take P as P5, P4, P3, P2, P1 and P0. So now we need to find the values of all the P's. So we will multiply the two numbers A2, A1, A0 multiplied with B2, B1, B0. We will similarly multiply it A0, B0, A1, B0, A2, B0, A0, B1, A1, B1, A2, B1, A0, B2, A1, B2 and A2, B2. Now we'll add the columns. Here we have A0, B0, A1, B0 plus A0, B1 and the carry of the first column will go here. So here we have C1 plus A2, B0 plus A1, B1 plus A0, B2 and the carry will go to the next column. Here we have C2 plus A2, B1 plus A1, B2. Here we have C3 plus A2, B2 and the carry will go to the next column, that is C4. So now when we find the values, we get P0 as A0, B0. We find P1 as A1, B0 plus A0, B1. And similarly, this is the value of P2. This is the value of P3, P4 and C4 is our P5. So let us draw the circuit of the 3-bit multiplier. Similarly, we'll write the numbers first, that is A2, A1, A0, B2, B1 and B0. We'll first draw P0. P0 was A0, B0, A0, B0. This is our P0. Then we have our P1, which is nothing but A1, B0 plus A0, B1, A1, B0 and A0, B1. We'll add them using a half adder. We have a sum and a carry. Now we have our P2. P2 is nothing but C1 plus A2 B2 plus A1 B1 plus A0 B0. A2 B0, A1 B1 and A0 B2. A0 B2. Now we will add the C1 with A2 B0 and A1 B1 using a full adder. Here the sum is our S dash and the carry is C dash. We'll take S dash C dash and A0 B2 and add them using a full adder again. Now we'll get our S2 and C2. It's time for us to draw the P3, which is C2 plus A2 B1 and A1 B2. A2 B1 and A1 B2. We'll add these three components using a full adder. Here we'll have a sum which is S3 and a carry which is C3. For P4 we have C3 plus A2 B2. A2 B2. We'll add C3 plus A2 B2 using a half adder. We'll have S4 and C4. So our S1 was nothing but P1, S2 was nothing but P2, S3 is nothing but P3 and S4 is P4. Our C4 is P5. So this is our multiplier circuit for 3-bit numbers. When you see, you can similarly draw the multiplier circuit for two 4-bit numbers where A is a 4-bit number, that is A3, A2, A1 and A0, and B is also a 4-bit number which is B3, B2, B1 and B0. You can follow the similar steps as we did in the 3-bit multiplier and you will get the multiplier circuit of the 4-bit numbers. Thank you.